Next speaker is P Millan from Universidad de Granada, and she'll talk about topology, synchronization, and brain dysfunction. So we stay in the neuroscience domain.
Thank you for the introduction. Here I wanted to exploit that this workshop involves both theory and applications to try to. Do you want to try? Okay. To try to talk about both of my main areas of work in the past years that involved hypergraphs of, well, really simplicial complexes in the most part. So for the applications, I'm going to be talking mostly about brain networks or higher order networks. So I wanted to have a slide giving some context of what's under a brain network, right? Because we always, at least from the physicist perspective, you have your nodes, you have your links, and you kind of forget that there is a whole world underneath. And the methods that you are going to use in the end really should remember where we were coming from. So of course, the idea is that, well, we have a head that has some function, it's doing something, and we want to represent this with a network because we have this idea that this is a convenient representation and we can gain some information back of the original space. How we do this? Well, we need to measure first this function somehow, and for this, I'm going to be talking about functional networks for this part. So about what Pedro mentioned as mechanism, not actual interactions. So if we are going to measure function, then we need to infer what's happening inside the head somehow. And for that, we have a lot of different measures. Some of these do measure the activity directly, like electromagnetoencephalography, and others infer it from other measures, like functional magnetic resonance. And here we have a trade-off. If we want a very large network, then this is going to have low temporal resolution, so it's going to be slow. So if we are going to look at task or functional data, perhaps it's not the best. And if we go to very highly temporally resolved networks, then typically these are going to be small, very small. So there's always this trade-off. Here, most of my examples are going to be relating to MEG and functional magnetic resonance, but this is more common. So let me very briefly introduce MEG networks to you. So we have this very expensive magnetoencephalogram, which is why I think this type of networks are not more common. We have a magnetically shielded room because the fields, the magnetic fields generated by brain activity are orders of magnitude smaller than the magnetic fields that are around us, especially in a city. So we shield that out, then we measure with a set of sensors, we measure the magnetic field there. Then somehow with a head model, you try to solve the inverse problem to get the activity at the brain itself, so in a set of brain regions. Again, this is still not a network, so we need another model to derive from the activity of the regions, the nodes, some connections. We have a lot of different measures to do this. Indeed, Pedro was introducing a family of these measures based on information theory. We have other sets based on synchronization or correlation between the signals. And what you get with them is not necessarily the same because the assumptions beneath them and what we are measuring with them is not the same. And of course, this was for pairwise. Once we go to high order, we still have to make this choice of how we are going to define or measure these higher order or hyper-edge interactions. To give some examples of the applications that we can do with a more clinical context, because I was working at a neurophysiology department at the hospital, so we were very interested into how we could apply these methods to treat neurophysiological disorders better. This is a study applying TDA to pairwise networks. And Fernando Nobrega Santos was the leader in this project. And what they did was apply a filtration process to study how the simplicial complexes at different dimensions were appear as one increases the threshold so the strength of the links that are included. Sorry, this is really making me dizzy. So as you can see here, we have the pairwise network when built by one-dimensional simplicial complexes or 2 cliques, then the triangular network and network made with tetrahedra. And what we can do here, of course, there are different things that one could measure, but relatively simple measure to do is the Euler characteristic. Why? Because this can identify the emergence of the connected component in each of the dimensions. So if we look at the zeros of the Euler characteristic, we can see when the pairwise network becomes connected, when the 2D network becomes connected, and so on. And this is what it looks like as this, the strength of the links and the density of links is increased. Sorry. The black curves are for different individuals. You can see there is a lot of variability in where the topological phase transitions take place. And overall, the average curve is the blue one there. But this can actually be useful because if we control this curve for healthy individuals with the one for patients with glioma, we find significant differences, particularly in the location of these phase transitions. So glioma is a very invasive type of brain tumor which has quite complicated expectancy. So the group by Linda Gao and Fernando, they are really worked in trying to gain more information in network theory on the prognosis of this type of disorder. So with this type of measure, what they found is that, well, they could, at the group level, distinguish the two cohorts, so the healthy individuals from the patients. However, you cannot use this to predict individually which patients will perform how. So for that, we would still need to improve or think of better different methods. This is another example where we now looked at patients with epilepsy. This was done again with the clinical neurophysiology department in Amsterdam, in collaboration also with Leonardo Di Gaetano in the Central European University, who did a lot of work analyzing these networks. So these patients with epilepsy they're resistant to medication, meaning they keep having seizures after being on medication. So the treatment of choice is the removal of a region, the red area here for this patient, with the hope of stopping the seizures. So you can see this is huge, right? For this patient, most of the left temporal lobe was removed. And in this case, it was a successful resection, so the patient didn't have any more seizures after that, but for about 1/3 of the patients, they can continue to have seizures after this. And the evaluation for this is very careful, right? They just don't just cut. There is a very extensive evaluation, a lot of different imaging modalities, extensive discussion. So they really try to find the best resection and only resect when they think the surgery will be good. But still, for 1/3 of the patients, this is not the case. So there's a lot of research to try to understand why and improve on this. Typically, one finds network-based analysis where we look at the properties of the resection area. For instance, here there's the between centrality of each region, and you can see that part of the resection corresponded with the strongest hub in the network. And indeed, it's typically found that removal of the hubs is associated with a good outcome. But it is not true in general. And removing the hubs can also be bad for function, right? They are also important for healthy activity, not only for the seizures. So to try to get together like some of these studies, conflicting studies that were in the literature, what we did was try to take a step forward and perhaps try a bit more complicated analysis in this case, since the simple ones were not enough. So what we did was that, well, since the seizures need to spread, they don't only take place locally, but the bad ones really spread throughout the brain. Let's look not only at the region that is removed or its local centrality, but let's consider its role in this neighborhood, in the extended neighborhood in particular. So we can look at what is the regional organization around these different brain regions. And let's consider this. Let's look at these regions in detail. So I want to see what's the centrality of this area, but also of its neighbors, because there's the idea that, well, it can be maybe you don't remove a hub, but you remove something that is connected to a hub, and that can be enough to stop the seizures. So we looked at these three different types of regions, the nodes that were resected, the neighbors, and the remaining nodes. And what one finds that indeed both, so if you look at the resected nodes, these are in general, for most of the patients, these are more central. So this is a bit complicated picture, but we have here several frequency bands of activity. We have here several metrics of what we call generalized centrality. Some of these are not centrality metrics, but please don't come at me. But we consider it as local metrics, the between centrality, the clustering, and the curvature. And as neighborhood metrics, the size of the neighborhood, so how many nodes are at distance 1 or 2 of each region, the number of links, and the three first Betty numbers of the simplicial complex that one builds over the neighborhood. The local measures were used as a to have some context to compare with previous studies, of course, and these are the most commonly, the between centrality and the clustering are considered quite commonly. So what we found was that, well, when we look at how central the resection area is versus the remaining of the network, with these neighborhood metrics, I said Betty 0, we find that for most patients, which is these blue triangles here, the resection area is more central than the rest of the network. And this is true for around 60% of the patients, but not for all of them, which again, we recover this heterogeneity between different individuals. And indeed, for some cases, we found these are the light red triangles that the resection area was not a hub at all. Now, if we look at the neighbors of the resection, this will surprise no one, but they are typically hubs. They are more central than other nodes in the system with any of the considered metrics. But what we also found quite surprising is that we cannot really distinguish, for most cases, the resection area from its neighbors. They tend to be equally and highly central. And this result actually tied very well with previous findings that, well, we find that for some patients the resection area is a hub, but not for others, so it's not very clear what's happening. Well, it turns out that if you consider this three partition, if you split the nodes that are not resected into the neighbors and the rest, then things become much more clear. And to see how much more clear, these are the results with the traditional analysis, where we don't find anything for almost any patient, except with the curvature. And I don't know why we find things with the curvature. If anyone has any hypothesis on this, I'm very happy to discuss them. I don't know what that one is, but we just consider curvature up to, so the links and the triangles, this is the Ricci, the local curvature, right? We got, yeah. Yeah, yeah. Maybe later we can look it a bit better. But yeah. So yeah, I'm happy to talk about why we find this and to explain it, because these results are really contrary to the rest of the measures. But yeah, overall, even though we could get a better picture of what the different nodes are doing when we try to predict if the patients will have good outcome or not, this is the result of the classification. You can see the numbers go only up to 70% with any of the metrics that we consider. So this is different frequency bands, different combinations of these scores of these results. Really, it's never very good. We get a 70% area under the curve, which is not, it's something, right? We are seeing an effect, but it's not something that can be used to at the individual level. However, for a group this size, we included 90 patients. This is much better than anything that could be done with these pairwise metrics and this traditional two-node partition. So we are hopeful that with a bit extended analysis, we can get a bit nicer results. So now I'm going, if you notice, these networks were all pairwise, right? I just built simplicial complexes on them, but we were only considering pairwise connections. but of course, Pedro made an amazing introduction to this because not everything is pairwise. Sometimes you can measure some effects that cannot be reduced to pairwise interactions. So we can distinguish between these synergetic effects, and I'm not going to introduce this because he already did an amazing introduction, from the redundant effect that can be, where the higher order interactions can be found in the lower orders. So in this study, again led by Fernando, we looked at how using this information theory metrics that Pedro was introducing, how the hubs are distributed. So again, looking at the most central regions, but now in these higher order networks. And then one can consider whether the hubs that one finds with the synergetic interactions are the same or they're different from the redundant one. And indeed, there are quite strong differences. We found that the synergistic hubs typically integrate cortical and subcortical regions. This was in agreement with previous studies. And then if one looks at more redundant hubs, then we recover other types of network. There are different types of information theory measures that one can use, and different networks that are well known from previous studies, from resting state studies, are found. In this case, for instance, using this total correlation between 3 sets of variables, one recovers the visual network. And depending, again, we found some correlations between the strength of these hubs and motor skills or cognitive skills of the individuals. In particular, if one looks at the strength of the hubs with this synergistic measure, that is the interaction information, then that correlates with how fast one individual moves. So here, one of the main points, I think, apart from understanding what different modes of information mean for activity, and this, of course, is general, not only for the brain. There is also something that I've been discussing with some of you already, that these matrices are very big, right? We go from these 2D matrices that one can see and kind of understand a bit more intuitively to higher dimensional tensors that really can hinder the interpretation of the findings unless one finds a way to reduce this information to something we can see, like looking at the hubs or looking at only a measure, a one-dimensional measure like synergy. But so this ends the introduction of very long introduction of the topic with the applications. I want to now move to the theoretical part of the talk, where we kind of forget where all the networks come from, and we look at the dynamics that these higher order networks can sustain. And I'm going to talk in particular about 2 types of dynamics that Ines already introduced in her talk, which are the topological synchronization model for not for the nodes of a higher order system, but for the hyper edges. And then I'll discuss briefly a model for percolation, including triadic interactions. So if we go to synchronization of hyper edges, now, of course, our dynamical variables are not on the nodes of a system, but we want to place them on the edges. Why? Well, because this is interesting, and also because the edges can also be dynamic. So in any transportation network, the dynamics will be placed on the edge. And again, going back to the brain, connectivity is not static. It can change as time. This means that the edges have some dynamics that may not be reduced to the nodes. So again, we already talked a lot about this, especially on Monday, but I'm gonna be using the framework of the Hodge Laplacian and the incidence matrices, which, so I will just very quickly remember these terms for perhaps anyone who is not very familiar with them. So we will consider simplicial complexes. These are higher dimensional structures that allow us to encode these higher order interactions in the data, and they have the closure condition. This means that all the lower dimensional phases of the simplicial complex are also included in it. We can define the boundary of the simplicial complex with these incidence matrices that takes us from a dimension D, in this case, a 2-dimensional simplicial complex, to its boundary in dimension D-1. And we have the property that the boundary of the boundary is null. So we cannot, let's say if we try to take 2 steps back, then we will get a null set. Then with this, one can write the Laplacian, in this case, the pairwise Laplacian in terms of this incidence matrices. Again, I'm sure this is very obvious for a lot of the audience here. But just to give some context, what we can interpret this product here as the boundary B1 transpose taking us from the nodes to the links, right? And then we go back to the links by applying the incidence matrix again. And this encodes the type of interaction of the nodes between the links. And of course, we generalize this with a Hodge Laplacian to higher dimensions, where now we have 2 ways of interaction. So we can, as with the nodes we interacted through links, we can now interact, the links can interact through triangles, for instance, or through the upper dimensional dimension with L up. But we now have another possibility, which is the interaction through the lower dimension. So edges can interact through the nodes as well. So we have now these 2 terms, L up, which is the direct continuation of the pairwise Laplacian, but we now have also L down, right? And this is going to significantly change dynamics. To remember some properties of this Hodge Laplacian, we know that its kernel is the corresponding Betti number. We have the Hodge decomposition that allows us to write any vector as the composition of the harmonic, rotational, and solenoidal component, and the harmonic component will be in the kernel. And of course, this L down and L up commute, and they can be diagonalized together. And this, I wanted to remember these properties, even though we already mentioned them in the previous talks, because they are going to be important to understand what happens when we use this formalism to expand the pairwise Kuramoto model to a higher order version placed on the edges of a simplicial complex. So here we have the well-known Kuramoto equation for synchronization. We can rewrite this as in terms of the incidence matrices. And of course, if we linearize this equation, then we recover the Laplacian. Now, this suggests how we can write the higher order Kuramoto equation, where now our dynamical variable, instead of being, again, on the nodes, is going to be on the links. And we have the 2 ways of interaction. We have interactions through the upper faces and also through the lower dimension. And if we linearize this equation, again, we can write it in terms now of the Hodge Laplacian of the corresponding dimension. So we simulate this model, in this case, for dynamics placed on the edges. And you find that actually they don't seem to synchronize if you look at it in the traditional way of the Kuramoto model, right? So we measure the synchronization between the faces of the edges as one increases the coupling, and they don't really seem to synchronize. What happens? Well, what's happening is that actually, because the harmonic component is in the kernel of the Laplacian, is not coupled by the equation of by this higher order Kuramoto equation. So each of the harmonic components of the vectors, if you project them, they evolve only according to their proper frequency, so they will not synchronize. However, the the rotational and the solenoidal components are coupled, and if we project the dynamics, so these are the original link dynamics, if we project them with the boundary operators in the upper and the lower dimension, so we go from the links to the dynamics that are created by the links but seen in the nodes and the triangles, then they do synchronize. And actually, we can write the equation for the nodes and the equations for the triangle, and these are the traditional Kuramoto equations. And indeed, using the corresponding synchronization parameters, we find this transition where now the transition point is at 0, so at coupling 0. And with phenomenological theory, one can actually recover, I will skip that, but one can recover the shape of this transition and the location of the transition point. So we are then seeing the synchronization transition when we go to nodes, when we go to triangles, but not yet at the links, which were our original space. But we can do this just by applying a topological filter, right? So if we filter the original signals by the up and down Laplacian, then we keep either the solenoidal or the rotational component, and this we can see that they do synchronize. These are the one shown here. So in this case, this highlights the roles of these topological filters that we also heard about in the first days of the talk. Because unless you apply these filters, you would not see that there is a synchronization happening on the edge signals. Now one can think, well, if we have these two dynamics on the nodes and the triangles that projected on the nodes and the triangles that seem to be decoupled, but we can, what happens if we couple them? For instance, by modifying the equation, and now we can modulate the interaction through the triangles by the synchronization at the node level, and vice versa. We modulate the interactions through the nodes based on what the triangles are doing. This means that when we project, the dynamics will no longer decouple. And what this means for the dynamics is that now, instead of having a continuous transition, we find an explosive transition due to the interaction that we have introduced between the two dimensions, the dimension of the nodes and the dimension of the triangles. Again, you can verify this finding and recover the explosive nature of the transition and the location of the critical point. And we found that this behavior was very general, and we could find it in a variety of networks. So the previous results were for the configuration model, but they also hold in simplicial complexes built from real-world networks, in particular the connectomes of the C. elegans and the Homo sapiens. Of course, now the transitions are smoother because these networks are smaller. And it also holds in different network models, higher-order network models, sorry. So to summarize, in this topological higher-order Kuramoto model, the coupling is naturally derived from the topology via the hot Laplacian. And depending on whether there is coupling between the lower and upper dimensions, we can find either an explosive or a continuous transition. In either case, we will only find this if we apply a topological filtering on the data. And to begin the final part of the talk, so we were talking about oscillators that don't seem to synchronize. Now we are going to talk about percolation that is dynamic and not static. And this is again an effect of having higher order interactions. So if we think about percolation in this network here, we will see, well, there are three components. Here we have the giant connected component, and that will be the end of the story. But what happens if we have an interaction that can turn links on and off? In particular, in this study with Ginestra and Hanlin, what we did was to have interactions that the nodes could regulate the status of other links with these triadic interactions. So a node could activate or deactivate other links. And then this creates another network in which the giant component can be different. And this giant component will determine which nodes will be regulators in the next step, which creates an intrinsically dynamical process. I will split this for a moment. And this dynamical process can look very complicated. So here I show in pink the nodes that are in the giant component under different with different noise levels. And as you can see, in these cases, we find the emergence of rather different spatial patterns and temporal dynamics. Why we're finding spatial patterns is because we include an aspect that is quite common in real networks, which is that interactions tend to be local. So many networks are grown in a geometric space with some geometric constraints based on distance, for instance. So if we consider this triadic percolation on a network that has a spatial structure, and both in the structural links and in these regulations, then we find that the percolation patterns become these interesting shapes, which have the different dynamics depending on their spatial distribution as well. So if we have a very high probability of random damage, then we will find that there are small clusters of active nodes that seem to diffuse over time. If we have very low probability of random damage, then we find these stripes, which are actually loops, because this is a torus with periodic boundary conditions. And this type of pattern we could explain through a minimization of the border. And then if we are in the middle, then things get a bit more complicated. And actually, one strong difference with traditional percolation that you can find is that the size of the giant component is not maximal when the noise is minimum. So here, this P is 1 minus the noise. So one would expect that the giant component, the size of the giant component goes to 1 as we decrease the noise, so the probability of random damage, sorry. But that is not the case. And we actually find that the largest giant component appears for intermediate values of the random damage, which is because of how this plays with the triadic interactions that can either activate or deactivate a link. Then we can look a bit on how this, the properties of these shapes, and in the spirit also of this workshop, we found that topological data analysis was a very good tool to describe the properties of these different types of patterns. Why? Because their topology is rather different. So here we have these cluster patterns. They are typically formed by one component. They have no loops. So you don't expect any when you look at the homology with using these persistent diagrams, you don't expect any points from H1 that are far from the diagonal, and indeed that's what we found. If we look at the stripes, we have now one loop and one component. And here is, in this case, this point corresponds to the loop quite clearly. And if we look at the octopus, things get more complicated. One can have multiple components that survive quite long in the filtration, and also multiple loops. So we can attempt to classify the patterns based on this. And we could, we had quite good results using topological data analysis to find, to describe the dynamics in time, so how the system is shifting from one pattern to another. And in this case, the different colors correspond to each of the 3 patterns. So as you can see, the patterns not only move in time, but we observe shifts between different topological patterns. In particular, here between these complicated patterns, which we call octopus, because, well, how they look like, and the stripes. And one can look at the temporal properties of these dynamics as well. Well, sorry, this is how the fraction of patterns in each class changes with the random damage. And we found that there's this sort of double transition or double change as the probability of random damage decreases to the right, you're right. We initially find only clusters, so these small patterns. Then as this, the probability increases, then we find the complicated shapes in the middle, right, when we have the most noise. And finally, when the system becomes more almost deterministic or deterministic, then it is dominated by the stripes pattern. And what I was trying to say before is that if we look at the time, sorry, I made an error here. If we look at the temporal properties of this, and we can look at the entropy, we can estimate the entropy through the complexity of the temporal signals based on this description in terms of the different patterns that they can show. We find that it has 2 peaks, which correspond nicely to the transition from the cluster-dominated to the octopus-dominated to the stripe-dominated regimes. And we find a variety of different temporal behaviors. So I've highlighted some here. These small clusters tend to diffuse more or less in a 2D space, whereas the stripes show a combination of periodic movements and also diffusion, and the octopus tend to show this, what we call short-term blinking, if I can show it, which is this blinking between a pattern and the contrary pattern, but because there is a lot of thermal noise in the system, this is not exact, and throughout time the patterns get destroyed. But we do also find, that there is a true periodic regime for some combinations of the patterns, where both the size of the giant component are and the location of the pattern, in the case of stripes, follow a truly periodic dynamics. And this goes on to show that, well, this is a complex system model with a lot of different possibilities. So you should go to Hanling's talk tomorrow to hear more details about it. And I would like to finish here, trying to gather together a few of the ideas from the 3 points that I introduced. And well, you're here in a conference about hypergraphs, so I don't need to convince you that we seem to be we find these higher order effects in many systems that can be that are of interest to us, and we still have a lot of questions to be asked of what these effects mean in terms of the dynamics, in terms of the behavior of the system, and how we can exploit them potentially for applications, perhaps clinical applications. And with that, thank you for your attention.
Questions?
Yeah.
For the synchronization, which Laplacian is more important, the up Laplacian or the down Laplacian?
Well, what are you looking at, of course, but I'm not sure I can answer that question. But in this case, both Laplacians are weighted the same, right?
Which one is contributing more?
Here.
You first take one and leave out the other.
What one is contributing more? Well, you have more interactions typically through the low Laplacian than through the upwards, but I don't know if I'm answering your question with that. Yeah.
We give some intuition why the giant component is not monotonic.
It's because of the negative regulation. So nodes can promote links, but they can also kill them, well, inhibit them. So you have this, because the regulations are local, where you have activity, you have inhibition. And this means that the giant component can never get too big. In these spatial systems, if the network is not spatial, then tomorrow you can see what happens. And then it can get, it's not monotonic, but then you can get bigger.
Yeah. Thank you. I have a question about the periodic patterns that you show in the scaling.
Yeah.
Is this any way affected by the fact that you are using periodic boundary conditions?
I think not. Well, perhaps the position, yes, that can be affected by that, because we look here at two things: the size of the giant component and its position. So the size you also recover in random networks and much the periodicity, I mean, and much clearly. Hanlin is the expert in that. For the size, I do assume you need some type of periodicity so that you don't see the effect of the borders, at least, or a very large system. Because in this case, the stripe is crossing the borders for sure. Yeah.
What is your consider orientation in the boundary setting, and then how you define orientation in your system?
Yeah, I rush through that a bit quickly. You mean the orientation of the simplices? Yeah, so we set an orientation based on an arbitrary labeling of the nodes, but once you set it, it's consistent, right? So the results are independent on the orientation that you set, as long as you should, yeah, everything is consistent with it. So you mean changing the sign of one simple or of some simplices? Yeah, yeah, I don't know. That would be interesting, but.
The synchronization fits the mono vectors. So I think for those doesn't matter much which direction you go. You have also the frequency.
if you only use Laplacian method, you use boundary operators, then sometimes you have trouble.
Yeah, but you use two boundary operators.
Yeah, you always go.
So orientation sign incorporated at the same time with equal weight.
Yeah, so the sine function is odd.
Yeah.
So.
But of course, it
as a matter of
would be
sine-
interesting to look at the situation where the orientations do not match.
Yeah, when you have a mismatch between the dimensions, that could be interesting. But
I think that is a very interesting question.
but I guess you could not do that. Like you would need to change quite a bit in how you build the model. Yeah.
You have a function that is not odd, right? So you have b sine b theta. So the orientation would not matter because you change one or the other. But if you have an odd function.
I think.
Other questions? Comments? No? Well then, thank you, Anna, once more.
Thank you.